So we've talked all about how using an orthonormal basis to define a subspace can be really helpful and save us a lot of time when we're solving different kinds of linear algebra problems. Now we want to go through the process we actually can use to turn a basis into an orthonormal basis, and that's called the gram-schmidt process. And what it does is it takes a non-orthonormal set and turns it into an orthonormal set. It's an iterative process, so we go one step at a time and we keep repeating the same process over and over and over until finally we've converted the last vector that defines the basis into an orthonormal vector. So as an overview, this is going to be a lot of formulas, but we're going to walk through it one step at a time. I just want to give you an overview of what this process will look like so you kind of know what we're getting into. So let's say that we are using the vector set v1, v2, v3 to define a subspace V. So we have the subspace V, it's defined with this vector set, and we're going to say that this vector set is not orthonormal, but we want to turn it into an orthonormal basis. So we want to define V using an orthonormal set instead of this v1, v2, v3 set that we've given. So the gram-schmidt process tells you that the first thing you want to do is start with the first vector v1, and you want to normalize it. So you're going to turn this into a vector that points in exactly the same direction, but it's just 1 unit long, so you're turning it into a normal vector. And you do that using this formula here. So to normalize v1, we just divide v1 by the magnitude of v1, and that gives us a vector u that points in the same direction as v1, but is 1 unit in length. So once you've done that, you can replace v1 with this new vector you just found, u1, and now you can say that v is spanned by u1 and then v2 and v3. So you've just modified the first vector to make it a normal vector. And you can do that because when you're defining the basis for a subspace, only the direction of the vectors matters. The length of the vectors is not really important, it's just their direction. So replacing v1 with u1, that vector points in exactly the same direction, it just has a different length. But that difference in length does not change the definition of the subspace V. So now you've got your subspace defined this way. Your next step is to work on v2. So we already took care of v1, now we need to work on v2. For every vector from here on out, you're going to first change the vector into a vector that's orthogonal to all the vectors before it. So in this case with v2, we're going to change it into a vector that's orthogonal to u1. And then once we have that orthogonal vector, then we'll normalize it. So to get it to be orthogonal, we're going to use the idea of a projection. And that projection is going to turn into this formula here for w2, where w2 is a vector that is orthogonal to u1. So then once we have w2, we'll use this formula up here to normalize w2, and that'll give us a vector which is both orthogonal to u1 and normal. And so at that point then, we'll have v defined by u1, u2, and just v3, where u1 and u2 are orthogonal to one another, and they both have a length of 1. And so we proceed on with this process, working on v3. This is the formula to turn v3 into an orthogonal vector, a vector that's orthogonal to both u1 and u2. Again, this will come out of the idea of a projection onto a subspace. So we'll use this. We'll convert v3 into an orthogonal vector, then we'll use this formula to normalize it and end up with u3. And finally, at that point, we'll have v defined in terms of u1, u2, and u3, where all three of these vectors are orthogonal to each other and normal. Now v is defined in terms of an orthonormal set, when we started with a set that was totally not orthonormal. And the idea is that you can keep going. This doesn't just work for vector sets of 3 vectors. It works for vector sets of any number of vectors. So if v was spanned by 10 vectors, we could continue on with this process, finding w4, w5, w6, etc., and each time normalizing the vector to continue on making each vector in the set orthonormal to all the other ones before it. And you see this pattern here with w4. This w4, of course, wouldn't apply to a 3-vector set, but I wanted to show it to you so that you could see this pattern here, where when we're working on, let's say up here, v3, we were working on the vector v3. To make it orthogonal, we have v3, the vector we're working on, minus, and then here you have the dot product of the vector that you're working on, v3, with the first normalized vector u1, and then multiplied here by u1, and then added to that the vector you're working on, v3, dotted with the other vector, u2, and then multiplied by u2. And then when you see you have w4 here, that means you would be working on v4 if you had that in the set. So you see you have v4 here. You have v4 dotted with all the vectors that come before it, u1, u2, and u3, and then multiplied by u1, u2, and u3. And this formula would just continue to expand, adding another one of these terms here, just adding on a whole extra term every time that we go on to the next vector. So just to give you an example of what this process looks like and walk through it, let's say that we have a subspace V, and it's defined by the span of, we'll use two vectors in R3, which means that V is a plane in R3. So let's say we have the vectors -1, 1, and 0, and then we have maybe, for the second vector, 2, 0, and -1. So we'll call these vectors here the vector v1 and the vector v2. And then the first thing we want to do is normalize the first vector. So we would want to normalize v1 using this formula up here. We'll first need to find the magnitude or the length of v1, and that'll of course be the magnitude of v1 is equal to the square root of -1 squared is 1, plus 1 squared is 1, plus 0 squared is 0, and that's going to be equal to square root 2. So the length of v1 is square root 2. To normalize v1, we use this formula, and we'll say u1 is going to be equal to, we just take 1 over the magnitude we just found, root 2, and multiply that by the vector v1, -1, 1, 0. And so the result there then is -1 over root 2, and then 1 over root 2, and then 0. So this here is our first normalized vector, u1, that we just found. And now we need to go ahead and replace v2 with a vector which is orthogonal to this vector that we just found. So to do that, we can use this formula here for w2, and we can say that the vector w2 is equal to, we'll say v2, which is this vector here, so 2, 0, -1, minus, and then we have a dot product here, so the dot product of 2, 0, -1 with u1, the vector we just found. So that's -1 over root 2, +1 over root 2, and 0. And then we have that multiplied by this vector u again. So -1 over root 2, 1 over root 2, and 0. So when we simplify here, we'll take the dot product inside the parentheses first. So we'll say 2, 0, -1. And then we'll subtract from that. Here we have 2 times a -1 over root 2. That's a -2 over root 2. Plus 0 times 1 over root 2 is plus 0. Plus -1 times 0 is 0, so plus 0 there, multiplied by -1 over root 2, 1 over root 2, and 0. Really, we could just rewrite this as 2, 0, -1, and then minus a negative cancels out, and we have plus 2 over root 2, multiplied by -1 over root 2, +1 over root 2, and 0. And so when we apply this 2 over root 2 now as a scalar to the vector u1, we get here, we'll keep our 2, 0, -1. And then here we're going to get 2 over root 2 times -1 over root 2. In the numerator, we'll get 2 times a -1, that's a -2. And in the denominator, we'll get root 2 times root 2, that's 2. So we get -2 over 2. Well, that's just equal to -1. And then here we get 2 over root 2 times 1 over root 2. That's 2 in the numerator and 2 in the denominator. That's a +1. And then here 2 over root 2 times 0 gives us 0. And so this will simplify to, now we just add the vectors, a 1, 1, and -1. Now that we have w2, we just need to normalize it. So first we need to find the length of w2. So we can say the length of W2, the vector we just found, is going to be equal to the square root of 1 squared is 1, 1 squared is 1, and negative 1 squared is 1. So we're going to get square root 3. That's the length of this new vector we just found. So if we then want to normalize this vector to make the vector u2, we just multiply 1 over this length by the vector. So we would say 1 over root 3 times the vector we just found, 1, 1, negative 1, and this is now u2. If we incorporate that 1 over root 3, we simply get here 1 over square root 3, 1 over square root 3, and negative 1 over square root 3, and that is our u2. Now for this problem, we're done because we just found we already had u1, we just found u2, but we only had to normalize and make orthogonal two vectors. We only started with v1 and v2. We've found our new orthonormal set, so we could say here that instead of defining v in terms of these two vectors, we could say that v can be defined by a different basis, this time an orthonormal basis, and we can define it as negative 1 over root 2, positive 1 over root 2, and 0 for the first vector. And then for the second vector, 1 over root 3, 1 over root 3, and negative 1 over root 3. Now the biggest question people normally have when it comes to gram-schmidt is how you can just replace each of these vectors with these new vectors and still be defining the same basis. It makes sense that the length of the vectors won't matter, but we're not just changing the length, we're actually changing the direction of the original vectors. The reason it makes sense is because of this idea of a projection. So remember the first vector, we normalized it and we found u1. If we sketch in a line, so we'll go ahead and just do a simple illustration here. So we'll sketch in a line like this, and then we'll define in here the vector u1 that we found. So we'll show this as the vector, and this is the vector u1. We'll call this the line L, and we can say that L is defined as the span of the vector u1. Because of course I can get any vector on L just with a linear combination of the single vector u1. And so L is a subspace, and then if we imagine that we have this second vector here, we'll call it the vector v2. So this is the first one where we change its direction. This is the v2 here that we're starting with, and when we turn the basis for v into an orthonormal basis, we actually do change the direction of the second vector. The reason that we can do it is because if we think about the projection of v2 onto L, so let's say that that projection looks something like this. Maybe it just goes to here. Okay, so this is the projection of v2 onto the line L. So we have the subspace L defined by the vector u1. We could say that v2 is projected onto L, and then that vector there is the projection of v2 onto L. Then as you know, as we've often said, we have this line here that can connect the projection to the original vector v2. And this is what we call here w2. This is where w2 comes from, is this vector here. And the whole idea is that we know that u1 lies in the subspace v because it has exactly the same direction as v1. It's just a different length. So we know for a fact that u1 is in the subspace v. And we know that v2 is in the subspace v because, of course, we're defining the subspace v with v2. We're using it to define v. So we know that both u1 and v2 are in the subspace of v. So what we're saying then is that w2 is a vector that connects u1 to v2. So by definition, it has to lie in the same subspace because even though it points in a different direction, it's on the same plane as u1 and v2 if it connects those two vectors to each other. So because of this relationship within this idea of the projection, we know that w2 is a vector that's guaranteed to be in v, but we would rather use w2 than v2 because w2 is orthogonal to U1. That's why we want to convert V2 to W2, because U1 and V1, they don't have an orthogonal relationship to each other. They're not orthogonal, so we can't use them together to form an orthonormal set. But U1 and W2, they are orthogonal to each other. So if we use W2 instead of V2, we're not actually changing the subspace V at all. We're not actually changing its definition. We're just picking a different vector instead of V2. We're picking a different vector to use so that we can start building out an orthonormal set, and W2 is orthogonal to U1. So that's why we find W2 using this formula here, and then we normalize it, and then we have U1 and U2, and we can keep going from there. The only difference is that as you keep going on to V3 and V4 and V5, the subspace adds a dimension. So here, to get U2, we're using W2, but we are projecting onto a one-dimensional subspace the line L. Once you already have both U1 and U2, so if you get to this point and you have U1 and U2 already, and then you're trying to find V3, this same concept applies, except that you imagine that U1 and U2 are in the same plane together, as opposed to U1 being on a line. You now have U1 and U2 in a plane. And then V3, you imagine is, instead of being a vector projected onto the line, it's a vector projected onto the plane, defined by U1 and U2. And then you find W3, which is the vector that connects the plane to the tip of the V3 vector. And that's where you get this formula here for W3, that vector. And then once you find that vector, you can normalize it. So you can see how Gram-Schmidt allows you to keep going through as many vectors as you have that define your subspace V in order to turn the basis into an orthonormal set.